All right, let's do some problems. And this is a practice exam. I wrote this. I really hope there are no typos. We're about to find out. And of course, practice is important. And the more you practice, the easier it is when you do it in real life. All right, so let's get going. Number one, find b so that the average rate of change of f of x, which is x squared plus x, between x equals 1 and x equals b, is 3 times the instantaneous rate of change of f of x at x equals 1. All right, this one is a little bit more than maybe you might expect, and a multiple choice problem, but not too bad. We have a couple of things. We have average rate of change, and we have instantaneous rate of change. All right, so let's start with this first part. Average rate of change between 1 and b. So that's f of b minus f of 1 over b minus 1. Okay, that's that first sentence. Our first part of the sentence is equals 3 times instantaneous rate of change, f prime 1. All right. Well, we can see, hey, f prime of x is 2x plus 1, and we can plug in 1. 2 times 1 plus 1 is 3. So that's 3 times 3, that's 9. Nice. All right. So then we have, what do we have? We have f of b. Well, plug it in. B squared plus b minus f of 1, 2 over b minus 1 equals 9. All right. Now you could work and factor this top as b minus 1. I'll just clear out the denominators on both sides. B squared plus b minus 2 cross multiplying equals 9b minus 9, or b squared subtract 8b plus 7 equals 0, and this will factor nicely because, you know, things should factor nicely. And we get two possibilities. One is, doesn't make any sense at all, and so that says it must be the other one. Lo and behold, 7. All right, so we circle 7. All right, good. Number 2, find the value c so that the following function is continuous at x equals 1. So what do we have? We have x plus 7 sine of x minus 1 over x squared minus 1 if we are not plus or minus 1. Now why plus or minus 1? We'll get to that. And then we're some number c if we are plus or minus 1. So essentially we have two holes. One at plus 1, one at minus 1. We're fixing the hole at plus 1. We don't care about minus 1. Now why is there a hole? Well, imagine you tried to plug in x equals 1. Downstairs, you have 0. Upstairs, you have 0. 0 over 0 equals more work. More work. Okay, so we can't just plug in 1. So what do we do? Well, so to plug in the hole, that really says we're thinking of removable discontinuity. Okay, so this is telling us, all right, we've got removable discontinuity, and possibly. Now, it might be that there is no such value. So, for example, if there was a jump or there was an asymptote, but we suspect removable. So we say, look, if we want it to be continuous, we need that c, which is f at 1, needs to equal the limit as x approaches 1 of f of x. Okay, that's just definition of continuity at 1, which is that's when I say definition right there. That's the limit as x approaches 1 of, well, we have x plus 7 sine x minus 1 divided by x squared minus 1. Okay, so that's the intuition. Now, I'm going to do this two ways. So, if you're doing multiple choice, which we are, here's the multiple choice argument. Because the multiple choice argument, you don't have to show your work. You say, oh, well, you know what? Sine has this really cool property. Now, we've already mentioned that this is going to 0 over 0, which is more work, so we have to do the more work. And here's the cool thing. It turns out that sine of theta is about theta if theta is small. So in other words, if what's inside is small, you can just treat it as though the sine of that thing is that thing. So say, hey, near x equals 1, x minus 1 is small, so this is about upstairs x plus 7 times x minus 1, and downstairs x squared minus 1 factors as x plus 1 times x minus 1. Cancel the x minus 1s, canceling the zeros, and then you say, okay, what do we have? Plug in 1. So this is about 1 plus 7 is 8, and 1 plus 1 is 2, so we get 4. So our answer is 4. Okay, so that's sort of the multiple choice. Now, what are we doing? Oh, hey, sign of something small is that something small. Now, I want to be absolutely clear. Suppose you see this in a long answer type question. So, okay, so a workout, we'll call it a workout, W-O for workout. Or maybe you might say, woe is us, for we have to do more stuff. Now, in that case, this will not get you full credit. So, what do you do? What do you do? Well, you need to use the fact that the limit as blah goes to 0, sine of blah over blah is 1. Now, you don't use the word blah, but you get the idea. So you say, okay, well, hey, this limit that we had before, we can write it as the following. We'll have it as sine of x minus 1, and downstairs you factor the x squared minus 1 as x minus 1. Upstairs you have that x plus 7, and downstairs you have that x plus 1. All right, so you rewrite it. And so you have a sine of something over something. Now you might say, well, what if I don't have this thing downstairs to begin with? You introduce it. You add it in. All right, just you need it in there. So if you have a limit and there's sine involved, 0 over 0, this is it. You got to go through it, get this kind of thing. Now what's the punchline? This says, hey, this goes to 1, this goes to 4, and so 1 times 4 is 4, and then you're good to go. Okay, so know how to handle limits that involve sign. So if you have a limit that involves sign and also involves more work, be ready. Sine blah over blah goes to 1. It's your friend. Use it. Great stuff. All right. Sorry, that one took a lot longer than I wanted, but we had to talk about how to handle various situations. So let's keep going. Find the tangent line at x equals 0 to the curve y equals e to the 2x minus 5 tangent x plus 3 cosine 4x plus x. All right, so what do we need? We need point, slope. Let's talk about our point. So just say plug in 0. So at x equals 0, what is y? Well, y is 1, tangent of 0, 0. Cosine of 0, 1. So 3 times 1, and x is 0, which is 4. So when we plug in x equals 0, we need to get out 4. Now we can use this to eliminate some options. We say, look, anything which doesn't have a 4 when you plug in 0 is out. So that would get 1, that would get 1, that would get minus 4. Boom, we're down to 2 options. So if nothing else, if we're pressed for time, we say at least we'll get a 50-50 chance. A lot better than a 1 in 5 chance. Okay, but now we say, okay, next step, derivative, y prime. And this is having us practice some basic derivatives. A little bit of chain rule mixed in. 2e to the 2x, 5 secant squared x, derivative of cosine, negative sine. But of course, since they can't check our work, if we write down positive sign, they'll never know. All right, that's the thing about multiple choice. They don't know. If you make a small mistake, as long as you get the right answer, on the long workout answers, they know. Oh, they look for everything. Okay, plug in 0. So at x equals 0, y prime is 2. Secant of 0 is 1, so minus 5. Sine of 0 is 0, and plus 1. 2 minus 5 plus 1. That's negative 2. So we say, that's our slope, so that means E is our answer. All right. Number 4. find the value of a for which makes, okay, all right, I'm not an English major, which makes the following function differentiable at x equals 0. So we're going to assume it's continuous. Now, because you can't be differentiable if you're not continuous, you can actually check if you plug in 0 onto both functions, you get the same value of 0. So in other words, we got matching up. Now, what does it mean to be differentiable? We can't have the matching up and have like a kink like this. Has to be smooth, right? The slopes have to match. So this comes down to saying that the derivatives match. So you say, okay, well, what do the derivatives look like? And you say, well, let's take the derivative of each side. Derivative of sine, cosine. And don't forget the 2 from the chain rule. So that'll be 4 times 2 makes 8. Cosine 2x, derivative of 1 is 0. Then minus, e to the 3x is 3e to the 3x. And that's if we're less than 0. Now, if we're bigger than 0, we'll take the derivative of a times x, which is a. All right. Now, here's the key. How do we know if we're differentiable is we need to be matching. So in terms of the limits, what we need is that the limit as x approaches 0 from below, f prime of x, has to match the limit as x approaches 0 from above of f prime of x. And well, we say, okay, what happens? As we approach 0 from below, well, we're this function. And we just plug in, right? Now, if we wanted to write down a lot of stuff, because we felt like we had lots of time, we'd write it out. But usually we just plug it in. Say, okay, plug in x equals 0. You get 8 times 1 minus 3 times 1, which is 5. And here, well, it's the limit as x approaches 0 of a, which is a. And so, a equals 5. So our answer is C. All right, good, good. So differentiable, the function has to match, and then the derivatives have to match. So just remember those two things, and you'll be good to go. All right, nice, nice. We're moving at a good pace, and that's important, because we want to make sure we get through our multiple choice and leaving in ourselves plenty of time, because those long answers are long sometimes. Number 5. Which of the following is not an asymptote for the function? So remember, there's two kinds of asymptotes. We've got the vertical asymptotes and we've got the horizontal asymptotes. Now, generally speaking, when we're looking for vertical asymptote, we want something that's not 0 divided by 0. A horizontal asymptote, we say, well, what happens as to, we should say f approaches what as x goes to plus or minus infinity. Okay, so here we go. Now, what do? Well, you plug in numbers. So let's plug in -2. We get 4 plus 8, which is 12, plus 3, and that's 15. Downstairs you get 4 minus 2 minus 2. So you get a non-zero number over a 0 number. Okay, so that's going to be a vertical asymptote. All right, plug in 0. Here you get 0, 0, 3, 0, 0, minus 2. Okay, that's fine. How about this one? 3 plus 2, 5. 1 minus 1, 0. You get non-zero over 0. That's a vertical asymptote. Okay, x equals 1. Okay, what do we have? 1 minus 4 plus 3. 0. 1 plus 1 minus 2. 0. 0 over 0. Now, 0 over 0 doesn't mean vertical asymptote. Now, it could mean it. This is a maybe. We haven't ruled it out yet, but probably we'll say, not only is it a maybe, it's actually a likely. So 0 over 0 usually means it's removable. So we say, okay, if we see that 0 over 0, we think removable. Let's just check these. Okay, now go to infinity. Now the nice thing is when you have polynomial over polynomial, you look at the leading terms, right, the growth. So this part's going to always go to 1. As you head to plus infinity, the constants don't matter, and you're going to head to 3 over 1. So this first part goes to 1, that part goes to 3. So y equals 4. Yep, that's good. That is a horizontal asymptote. So that's out. Now as you head to minus infinity, the e to the x's disappear and you get minus 2. 1 minus 2 is minus 1, so that's a horizontal asymptote. So yes, we were right. That 0 over 0 was indeed not a vertical asymptote. And we don't need to say what it is, right? We just need to say, look, we ruled out the rest. And it turns out you can factor x minus 1s out of both and get cancellation, so that's why it's removable. Okay, our last multiple choice. Find h prime of 1, given that h of x is g of f of x minus f of g of x, and the information in the table below. All right, so notice we need to take a derivative because we see that prime. So this is testing our rules. So h prime of x equals, chain rule, right, derivative of the outside, leave the inside alone, times the derivative of the inside, f prime of x. Subtract, all right? Then we get f prime of inside, g of x, times the derivative of the inside. Now, we're going to plug in 1. H prime of 1. That's g prime of f of 1 times f prime of 1 minus f prime of g of 1 times g prime of 1. Just put in what you know. What do we know about f of 1? We come to our table. F at 1 is 1, so that's g prime of 1. F prime of 1 is 3, right? I'm looking for f prime's row. I'm looking for value for 1, and I see it's 3. Minus f prime, g of 1. G of 1 is 3. So f prime of 3. G prime of 1 is 1. Okay, so g prime of 1 is 1 again. Okay, so 1 times 3 minus f prime of 3 is 4. So we have 1 times 3 minus 4 times 1. That's 3 minus 4. That's minus 1. And hey, that's an option. Woohoo! And there we go. All right. Whew. Done. We made it through our multiple choice. Nice. Nice. All right. Well, on to long answer problems, right? Yeah, you know it. Okay, good. And we have some instructions, but basically the important thing is we've got to show work. We've got to show justification. So we've got to do the work. Okay, number 7. Consider the graph below shown for the function g of x. Say, okay, all right, that's a nice graph. What do we need? Part A, find and classify as jump, removable, or other the discontinuities of g of x. Now, we look at it and say, okay, hey, you know what? We can spot the discontinuities. So we say, look, there's an issue here. There's an issue here. And we already know what the answer is because we can see the type of discontinuity from the visual inspection. So what discontinuities do we have? We have 2 jump discontinuities, right? Because there's a jump. There's a jump. So we say, look, okay, we know at x equals -1, we have a jump. And why? Well, because when we come in from the left, here's from the left, we approach -1. So -1, which is the limit as x approaches -1 from below, right? The -1 from below, those mean different things, of our g of x does not equal the limit as x approaches -1 from above of g of x. And what is that? Well, as we approach from above. So remember, when we talk about approaching, we're talking about coming in the x direction. And so from above, we're coming in to what value? 4. So that -1 does not equal 4. So if the 2 sides don't agree, that's jump. So that's the verification for jump. At x equals 2, well, we again have a jump. Why? Well, again, we're going to talk about our coming in. So as we come in from the left, so we're coming in from this direction, so we're following down here. What do? We're approaching 2. So 2, which is the limit, as x approaches 2 from below of g of x, does not equal the limit as x approaches 2 from above of g of x, which is, so as we come in from 2 from the above, we are approaching 1. All right, so that's it, right? That's part A. So we can find from the picture, we know where the discontinuities are, and then we say, cool. And so we can see the type of discontinuities, cool. And so the justification is knowing how to say, oh, what's the jump discontinuity? The limits from both sides don't match. Okay, there's part B. Consider the function h of x, which is you square g of x and subtract 3 times g of x. Now for each location, so we have 2 locations, determine if h of x is continuous. If not, then also classify the type of discontinuity. Use limits to justify your answers. So let's just work it out up here, what's going on. So remember, we have that h of x, that's our g of x squared minus 3g of x. And now we say, hey, what's happening? Well, as we approach from here, well, we say that what's going to happen? Well, we're going to go to negative 1 squared. And let's see, we'll do some work here. Negative 1 squared, subtract 3 times negative 1. Well, what is that? That's 4. Now, what happens is, what about here? Right, we can just do that. And, well, that's going to be what? We are coming into 4 squared minus 3 times 4. So, what's that? 16 minus 12 is 4. Those now match up, right? So the values match up. So that means, hey, there's no longer a jump, but is there a discontinuity? Well, when you plug in, what do you get? You're going to get 3 squared minus 3 times 3. Well, that's 9 minus 9, which is 0. That doesn't match up. So this right here is going to change. What do we now have? So the key here is that at x equals negative 1, it's become removable. Why? We have that 4, that equals the limit as x approaches negative 1 from below of h of x. And we can even spell it out here. This is the same computation. Negative 1 squared minus 3 times negative 1. We have that 4 equals the limit as x approaches negative 1 from above of h of x. Okay, that's 4 squared minus 3 times 4. And, but we have that, and that h of negative 1, got ahead of myself. H of negative 1 is equal to 0. So the limit exists, but doesn't match the value. So that's removable. So you say, okay, how do you know if something's removable? Limit exists, but the value of the function doesn't match. Now, there's one other point we have to talk about, which is what's happening here. Okay, so we had a jump discontinuity became a removable discontinuity. Now here we have a jump discontinuity. What's going to happen? Well, what do we see? We have from the left, we're going to 2. So if we plug that in, 2 squared minus 3 times 2, that's negative 2. From the right, we're approaching 1, which is 1 squared minus 3 times 1, which is negative 2. And then at 2, well, it's like we plug in 1. So everything is great. So what does that mean? So that tells us the following. Namely, it says, oh, you know what? At x equals 2, we're continuous. And how do we know that? Well, because we get that negative 2 is the limit as x approaches 2 from below. And That's because as we approach 2 from below, we're approaching 2 squared minus 3 times 2. Negative 2 equals the limit as x approaches 2 from above, h of x. That's 1 squared minus 3 times 1. And h of 2 is equal to negative 2. So that the limit exists and matches the value of the function means continuous. Limit exists and doesn't match means removable. And there we go. Okay, good. So we actually got to see, the whole sort of array. We got continuous, removable, and jump. Those are the three main ones. Almost never do we see other. That's just messy. All right, well, whew. Okay, we still have plenty of time, plenty of problems. Let's keep going. Number 8, use the limit definition to find f prime of x, where f of x is 1 over 3 minus 2 root x. Now, I'm going to be really blunt. They are very picky about these problems. If you do not use the limit definition, you will not get the points. And I will also say they love these problems. So be ready for limit definitions to show up. So it's like you know it's coming, and if you know it's coming, well, then you'll be ready for it when it shows up. No surprises. And we like it when there's no surprises. Okay, so these always start the same. We say, look, what is f prime of x? We write down the definition. In this part, we almost need to know nothing about the function. Limit h goes to 0. F of x plus h minus f of x over h. Notice in this case, we're looking for f of x in general. Sometimes you may be saying, oh, find the derivative at a particular location. And so like maybe f prime of 5. Then it would be 5 plus h minus f of 5. It's okay. Either one, same thing. Just write down the definition. So this step is always the same. And this is worth a point or two. So I got to get this right. Now, the next step. Know what it means to plug in x plus h. So what does that mean? Well, we're going to have the limit as h goes to 0 of, and now you write down the function. The only thing that happens is wherever you see an x, there's only one x, you put x plus h. So 1 over 3 minus 2 square root x plus h minus 1 over 3 minus 2 square root x all over h. Okay, now let's put in our mindset. What's our mindset? And essentially, we always have the same thought when we're doing these problems. It's always the same thought going through our heads. We're like, cancel some h's. That's always our thinking. That's our mindset. We are canceling h's. So you might say, well, wait, how do we cancel h's? There are no h's to cancel. There are no h's to cancel yet. So we got to make some h's to cancel. We have an h downstairs. What we need is an h upstairs. So we're going to be doing algebra. Now, algebra is going to consist of a couple basic tools. So make sure you know some tools. Know how to expand, how to factor, how to add fractions, how to deal with square roots. Spoiler alert with square roots, because we know that's coming, conjugates. So if you see a square root involved, you know there's a conjugate going to show up at some point. Okay, so first off, how do we add fractions? Well, common denominator. So we have the limit as h goes to 0. And here we'd have 3 minus 2 root x divided by 3 minus 2 root x plus h times 3 minus 2 root x. Okay, that's the first term. Minus 3 minus 2 root x plus h divided by 3 minus 2 root x, 3 minus 2 root x plus h. All right, so that is, we've gotten the common denominator, so we're ready to add at the next stage. This h, don't forget it. And since I don't like fractions within fractions, I'm going to move this h upstairs. Now, the way you do it is you flip it over. So it's a 1 over h. All right, good, good. And always keep remembering to write down the limit. If you forget it, Might lose a point. We don't want that. All right, so we have limit h goes to 0 of downstairs don't expand. There's no use to expand. We like the fact that there's an isolated h. So we have some terms here. 3 minus 2 root x, 3 minus 2 root x plus h. Upstairs, well, we're going to combine. Now notice what's going to happen. We're going to have 3 minus 3. The 3's cancel. Then we have what? Minus 2 root x plus 2 root x plus h. So I'm going to write that as 2 root x plus h minus 2 root x. All right, cool. Now, the numerator is probably the part that may throw you off the most. So let me just say, we'll work it out to the side here. And what happened for that numerator is that we had 3 minus 2 root x, subtract 3 minus 2 root x plus h. And then so that's 3 minus 2 root x minus 3 plus 2 root x plus h. 3's canceled, and then you just swap the order. Okay, now, the moment of truth. We've come to getting the h. We've got to get that h outside of that square root. Right now it's inside the square root. It's like, no, that's not where we want you. We want to free you. So if you have square roots, got to use the conjugate. So we're going to multiply by 2 square root x plus h plus 2 root x over 2 square root x plus h plus 2 square root x. So we do need to have that, basically flip the sign, right? And we do it top and bottom. We can't just square something, but we can always multiply by 1. So this is why it's like, we're multiplying by 1, so we haven't changed the expression. We've only changed how we write it. Okay, I guess you could say we've changed the expression, but we haven't changed the value. All right, so here we go. Downstairs, we're getting a lot of stuff building up downstairs, but upstairs it's great. When you use the conjugate, what you're really secretly doing is you have a minus b, a plus b. Now what happens if you take a minus b times a plus b? You get a squared minus b squared. So we have 4 times x plus h, and then minus 4 times x. All over, well, all this stuff downstairs. Again, we're not going to multiply out the downstairs because it doesn't help us. If anything, it obfuscates things. And we don't want obfuscation. We want clarity. Okay, well, what comes next? We simplify the upstairs. We have 4x minus 4x. So that leaves us with those cancel. So this leaves us with the 4h upstairs, and then h downstairs, and all these other pieces. All right, well, we're running out of space, but that's okay. We're also running out of problem because we've reached the moment of truth. We've done our job. We got to a point where we can cancel h's. If you do not get to a point where you can cancel h's, you need to check your algebra. This is algebra. I mean, a lot of calculus is algebra with a little bit of extra candy coating. So if you're not able to get to here and you say, hey, my h is canceled, woo, if that's not happening, check your work. Something has happened. All right, so the happy thing is, once we've canceled our h's, we've fixed our 0 over 0. We've done the more work. Okay, so we should celebrate by writing down the answer. So what do? We plug in. So we're now ready to stop writing the word limit. We can say, look, this is, plug in h equals 0. Upstairs we get 4. Downstairs we get 3 minus 2 root x. Here, this x plus h becomes x. So this becomes 3 minus 2 root x. And here we get 2 times the square root of x plus 2 times the square root of x. Now, we can do one little bit more round of simplifying. Okay, notice that this 2 root x plus 2 root x, this is the same as 4 root x. And then you say, oh, I have a 4 upstairs and I have a 4 downstairs, so that cancels. So we really have a 1 upstairs, a square root of x, and a 3 minus 2 square root of x quantity squared. And there we go. All right, so we took our derivative, we used our limit definition. And if you're wondering, is this the kind of level of difficulty that we might expect? I would say this is slightly harder, but you should be able to do these kinds of computations. If you just follow through step by step, you say, well, nothing's actually too bad, right? Definition. Know how to plug in x plus h. And then do algebra. Add your fractions, multiply by conjugate, just keep working it through. And you might say, when do I know when to multiply? When do I know when to not multiply? And the answer is, you multiply and expand it if it helps. If it doesn't help, don't do it. Be smart. Don't start. All right. Now, there's a part B. Use appropriate use appropriate differentiation rules to find f prime of x, where f of x is 1 over 3 minus 2 root x. They might say, didn't we just do that? Yeah, but notice this used limits. Part B is saying, don't do limits. Do it some other way. So we say, we have rules like chain rule. That's a great rule. So let's think about this function. First off, I want to write this in a slightly different way. Because it's 1 over something, I'm going to write this as something to the minus 1 power. And moreover, square root of x, beautiful thing for algebra, which is why we kept it square root of x up here. But for calculus, not so friendly. For calculus, we like to write it in terms of something to a power. So we'll write this as 3 minus 2 x to the 1/2 power. So this is the same function written in a way friendly to our rules. And we want it to be friendly to our rules because then life will be a little bit simpler once we apply our rules. Okay, so we've got a little bit of a function inside of a function inside of a function. So let's start slowly unraveling, peeling our onion. So our outside function is something to the minus 1. So remember, whenever you see something to a power, you say, oh yeah, that power is going to go down in front. So we have minus 1. The inside stays the same. Then minus 1 minus 1 times the derivative of the inside. Well, the derivative of 3 is 0. So 0 minus 2. And the derivative of x to the power 1/2. Well, same idea, right? Well, so you have this sort of 1/2. That's going to come down. So we have 1/2 x to the 1/2 minus 1. Okay, let's clean it up. Now, what do we see here? This is a minus 1. And now we'll start rewriting it in algebra language. 3 minus 2 root x to the minus 2. And then here we have a minus x to the minus 1/2. Now notice minus minus makes plus. And then we say, well, we have things to negative exponents. So that means they go downstairs. X to the minus 1/2 means you have a square root of x. Something to the minus 2 means it's downstairs as a to the 2. And there we go. There's our derivative. And notice it looks a lot like what we did before. That's not a coincidence. It has to look the same. So if these didn't match, one of these two had a mistake. And so that's a chance to say, oh, whoops, these aren't matching. Let me see if I can find my mistake. Now, looking at this, you might start to say, oh, you know what? This really helps see why, yeah, sure, there's a limit definition, but boy, rules are nice because this seemed to be a lot faster. Yes, that's the whole point. We want things to be fast. We want things to be straightforward. So that's why we're putting all this energy into our rules. Okay, well, that was number 8. Using limit definitions. An oldie but a goodie. They love putting that on the test, so be ready. Okay, number 9. Find A and B. Oh, classic. Finding two things, two equations, two unknowns. Here we come. Life is good. All right, sorry. Anyways, find A and B so that the curve y equals ax squared plus bx will perpendicularly intersect y equals x cubed at x equals 1. Okay, now, there's a note. Two curves are said to perpendicularly intersect if their tangent lines are perpendicular. So we're like, oh, okay. So this comes down to understanding what we need to be true about what's happening at 1. Now, first off, curves have to intersect. So there's we're putting a lot of emphasis on this word perpendicularly, but we also need to remember that there's this word intersect. So how do we know if two curves intersect? At a location, they have to match. So for intersection, what do we need? We need that a times 1 squared plus b times 1, that's the y value at 1, has to match 1 cubed, which is that y value at 1. Or we need a plus b to be 1. Okay, that'll guarantee an intersection. Now, that's not enough to guarantee that the intersection is going to be of the perpendicular flavor. So we say, okay, cool. Now we need to talk about our tangent lines. And so we need to have the tangent lines be perpendicular. So what we're going to do is take a look at our slopes. So we'll start with x cubed. Y equals x cubed. We have y prime is 3x squared, take the derivative. And so at x equals 1, our slope is 3. All right, now for this other curve, y equals ax squared plus bx, we have that y prime will be 2ax plus b. So at x equals 1, our slope is 2a plus b. Now, how do we know if two slopes are perpendicular? They have to be negative reciprocals. So we say, okay, this tells us that we need 2a plus b to be negative 1/3. Right? So just remember, perpendicular, negative reciprocal. By the way, what is parallel? Parallel means same. So know those two. All right. So what do we have? This is great. We have one of our favorite things. We have two equations. 2a plus b equals negative 1/3. A plus b equals 1. So now we look to combine. So we can do some add, subtract, substitution, anything we can do to cancel off a variable. Because two equations, two unknowns, that's great. But you know what's better? One equation, one unknown. Yes, that is way better. And so we say, okay, can we knock out a variable? Well, since they both have a b in it, let's just subtract, right? Well, what would happen? B minus b would be no b. Gone. 2a minus a. Minus 1/3 minus 1 is minus 4/3. So we now know a. All right? Well, let's suppose we know a. We can plug it in. Minus 4/3 plus 1, plus b, minus 4/3 plus b equals 1. Then we move that across. We get b is 4/3 plus 1, which is 7/3. So we now know b. Wait, we're done, right? Because what does the problem ask? You know, sometimes we get lost and we say, wait, where did we stop? Our goal was to find a and b. Okay, so we found A, we found B. So let's just write it one more time. A is negative 4/3, and B is 7/3. And we are done. We found it. We found it. So in general, if you're asked to find an A and a B of something, and I know at least one person who loves these types of problems. It's me. I'm the person. I love these types of problems. Okay, so anyways, if you see where you have to say, oh, I've got to solve for A and B, then you know it's like, I need to come up with two things. And so part of this problem is understanding like what two things need to be true. So it's like, okay, I got to intersect. That gives me a condition. I've got to be perpendicular. Oh, that gives me a condition. And so I have two conditions. And then what does that imply about A and B? That gives me two equations, and then I solve. All right, classic problem, beautiful problem. And, well, who knows what the future holds? We'll know soon enough. Okay, so, good, still plenty of time. Last problem. A particle's position is given by 2t cubed plus 3t squared minus 72t plus 17. Find the acceleration function a of t for the particle. All right, so what do we have? We have acceleration, and we want acceleration, right? But what do we have? We have position. How do these relate? Well, if you start with position, you say, how is position changing? Change in position is velocity. But what does change mean? Change means derivative. Okay, so to go from position to velocity, take a derivative. Now, if I'm at velocity, what do I do? Well, if I say velocity, change in velocity is acceleration. So to go from velocity to acceleration, take a derivative. So I'm 2 steps away. I need to take 2 derivatives. All right, so we have a plan. So we're going to take 2 derivatives. So we say, okay, s of t, 2t cubed plus 3t squared minus 72 plus 17. You see, I copied it down. All right, so step 1, s prime of t is 6t squared plus 6t minus 72. And the 17 goes away. Nice, nice. Ah, lovely, lovely. Now that's velocity. Okay, s double prime of t is 12t plus 6, and 72 goes away. Good, good. All right, and what did we say? S double prime of t was our a of t, and so there's our acceleration. All right, now, part B. Determine the intervals for which the particle is moving left, right? To the left, to the left. When is the particle moving to the left? We have to find that somehow. We've got to know that somehow. Okay, all right, sorry. We got to focus, right? Focus! Focus! Okay, so how are we going to focus here? Well, we have to understand the question, right? So it's about the particle. So we have lots of information here. And it says moving left. Now the question is, which one of these 3 gives us information about moving left or right? So position tells us location. Acceleration tells us how quickly, what's happening to our velocity. Are we speeding up, slowing down, changing direction? Movement is velocity. So we need to be focusing not on acceleration, we need to be focusing on velocity. Okay, so now we have to say, okay, so we're after velocity, and what does velocity tell us? Well, it's a number, right? And so we have to say, well, how does a number tell us how we're moving? Isn't it just tell us how fast we're moving? Well, that's speed. Speed tells us how fast we're moving. Velocity has a little extra something. So what's the difference between speed and velocity? Velocity has direction. Wait, what? How? Well, you have to remember that velocity can be positive or negative. And now we think about, oh yeah, right. So what's the difference? Well, if we're positive, we're heading to the right. If we're negative, we're heading to the left. So this part is really testing us. Do we understand which one of the functions do we need? And do we understand what we're looking for in that function? So this can be translated as the following. So we can retranslate this as says, when is our s prime of t, which is our velocity, negative? Okay, all right. So that is actually a big conceptual leap, that they like testing us on these big conceptual leaps. All right, so now we have a better idea of what's going on. So let's give ourselves a little bit of space. We'll make sure we still see our velocity function. All right, so let's look at our velocity function. So we have s prime of t. Well, notice somehow suspiciously it looks fairly nice. So we say, all right, factor out a 6. And that becomes t squared plus t minus 12. All right, well, does that factor? Amazingly, it's, one of the things you might leave this class is like, all polynomials are nice, they always factor. No, most polynomials don't factor, or if they do, they don't factor very nicely. But when we don't let you have calculators, we have to give you things that can work. So you should be suspicious. It's like, does this factor? It probably does. And so you should look for that. Now let's check. I claim it's t plus 4 times t minus 3. T squared, that's good. Minus 3t plus 4t is indeed t, and minus 12. Okay, so let's start by saying, when does this equal 0? All right. Well, that happens at what times? T equals negative 4 and t equals positive 3. All right, so here we go. Let's draw our number line. So we know we have 2 points, negative 4 and positive 3, and we happen to know that negative 4 becomes before 3. And so now we say, well, what's happening to our derivative, our velocity? Well, we have to look at our signs. So we say, okay, let's look at s prime. So s prime in below negative 4, s prime between negative 4 and 3, and s prime above 3. Now, how do we figure out the signs? Well, the answer is you plug in a number. Which number? Any number. The interval works. From negative 4 to 3, oh, how about 0? Okay, 0, 0, negative. Oh, very negative. Okay, how about something bigger than 3? 1,000,000 or 4? Yeah, either one. Or maybe 10. How about 10? 10's an easy number to work with. 600 plus 60 minus 72. Okay, well, that's positive. So we say, okay, s prime is positive. All right, how about below negative 4? I like that 10 thing. Let's do it again. So negative 10. Negative 10 squared, 100. 600 minus 60 minus 72. Positive. All right, so we can look at the signs of velocity. So what's happening? We see velocity is positive. That says we are moving to the right. And then we actually slow down to 0. That means we pause. And then our velocity is negative, so we are moving to our left. Again, then we slow down, stop at 3, and then we start moving to the right again. So we're zigzagging, right? So we're going right, left, back, right. Okay, so when do we move right? The intervals, and in particular, well, we're after the intervals of time. It doesn't explicitly state that, but that's the only thing that we could really hope for. So we move left for negative 4 less than t less than 3. So there's just a single interval. And there we go. So this one was not bad if you look at the computations, but of course the conceptual part, it tests us a little bit, right? And I think this is part of what makes this course challenging, especially the start of this course. When you step back and say, you know, none of these computations are particularly bad, but there's a lot of concepts. And if you're not comfortable with the concepts, it really can come back to haunt you. So what you want to do is say, look, let me understand what's going on. Because if I understand what's going on, then I can do the math. Like, I can do the algebra. I know you can. You're great. You're wonderful. You just have to make sure you nail down those concepts. So keep working it. I believe in you. I believe in what you can do. So I hope it goes well. Keep your studying. It'll be all right. We'll see you on the other side. All right. Bye.